Hello and welcome to my presentation. My name is Matt Bandy and I'm with a company called Resi. And I'm going to talk to you today about using drones and AI for wildlife surveys, and specifically the kind of wildlife surveys that are often required for compliance projects for solar projects, particularly in the arid environments of the western United States. Word about Resi real quick. We are a small company and we focus on applying modern tools like drones, artificial intelligence, computer vision to make field data collection better, faster, safer, and more efficient. And just to give you a sense for what that means and the kind of thing we're talking about, this is an example. This video is a downward facing drone video that we collected in Nevada earlier this year. And the colored rectangles are actual AI identifications of three resource types. The blue are Joshua trees, the green are Mojave yucca, and the red are dead Joshua trees. And you can see it's able to identify, it's analyzing this video frame by frame, and it's able to identify the objects pretty much in real time. So obviously, if you're mapping these kind of resources, there's a real time and efficiency advantage to be had in applying this kind of drone method, because obviously we're doing this much more quickly than you could do on foot using traditional methods. So while this isn't the actual method I'm going to be talking about today, I think this video really serves to show the potential of the method and some of its potential applications. So to do the kind of wildlife surveys that I'm talking about, there are a couple of steps. The first step is, of course, the drone survey itself. And in this step, we program drones to photograph areas of interest at a consistent elevation using terrain following methods. Usually the elevation is pretty low. The exact flight elevation depends on the size of the target resource, of course. So for larger targets, you can fly higher. And for smaller targets, you have to fly lower. The higher the flight, typically the faster the coverage. So depending on how high the drone is flying, it's moving anywhere from 2 to 15 times walking speed. So a significantly faster coverage, more or less regardless. And just to explain this image, each of those yellow rectangles is the footprint mapped on the ground of an aerial drone photograph. The second stage is to apply a computer vision algorithm to detect your targets of interest in the drone photographs. You do this by training a neural network to detect the targets. A variety of platforms are available that can do this for you. We use a platform called PyTorch, which is a software product that was developed and open sourced out of Facebook's AI group. There are other platforms. Google has one called TensorFlow, for example. So what you do to develop a trained neural network is you essentially tag a bunch of images with the objects of interest, with examples of what you're looking for. So here are some examples of avian carcasses in drone photographs. And again, just to give you kind of sense for the quality of the imagery we're talking about as well. And some more examples. On the top you have sort of pigeons and doves, and on the bottom bats. So you tag a bunch of photographs, you develop a lot of examples in a training data set, and you feed that to the neural network, and the software trains itself in terms of how to distinguish the objects of interest from other objects in the photographs. Another thing worth mentioning in terms of how we develop these models, we configure our models to maximize recall versus precision. So these are two performance metrics for object detection models. Recall refers to how many objects you actually find. So high recall means you don't miss much. Precision refers to the number of false positives. So high precision means you have few false positives. Typically, for the kind of wildlife surveys we're talking about for endangered species or avian carcasses, it's much more important to have a very high recall rate than to have a high precision rate. That is, you want to miss as little as possible, and it's worth sorting through a bunch of false positives to make sure that that's the case. So again, to achieve the kind of recall results that we have and that we really need to be effective, we do that at the cost of precision. So all of these methods involve a manual step of sorting through the detections to identify the true positives and eliminate the false positives. The final step is to geolocate the true positives once you've identified them. This image sort of shows an example of that. Again, the yellow rectangles are the ground footprints of the drone photographs, and all the little dots are geolocated detections. This is from a training example that we did in New Mexico earlier this year, so that's why there's so many altogether. Once the images have been geolocated, if desirable, you can perform field inspection and verification. All of these steps can be performed in the field if you have a sufficiently robust laptop and a trained person who can operate the software. You can actually perform this whole process with about a 30 to 60 minute delay in the field. So you can do detection, survey detection, and field inspection all in the same day, which is important for applications like avian mortality. We've trained a number of models and done some tests using these models. The first I'm going to discuss is an avian carcass model. We trained this on bird carcasses and bat carcasses, sample size of 166 for the birds, 142 for the bats. The model performs very well, about a 99% recall, 93% precision, as it says up there. And then we conducted 3 days of searcher efficiency trials in New Mexico using small birds, medium birds, and bats. The pedestrian survey walked transects at 6 meters, and we flew the drone at a 7-meter flight elevation. This photograph actually shows one of the trials in process. You can see the pedestrian surveyor to the right, the drone flying above him. I apologize for introducing a photo of wind turbines to this symposium focused on solar projects. But we did this in the vicinity of a wind farm. Just to emphasize how this trial worked, the drone surveys and the pedestrian surveys were conducted on the same plots at the same time of day with the same carcass setouts as the pedestrian surveys. So they were done in exactly the same conditions, same lighting conditions, same carcass positions, everything. So it's a very strict side-by-side comparison when we get around to making that comparison. Here are the results. You can see the sample size for bats is not tremendous. It's 14. So our conclusions are a little bit limited in terms of bats. For medium birds, sample size of 24. For small birds, 59. And you can see the results a little better when presented graphically. So for the medium birds, the box plot on the left is the drone searcher efficiency. On the right is the pedestrian searcher efficiency. So you can see the drone searcher efficiency is over 80%, pretty robust and significantly, larger than the pedestrian survey, which is more in the sort of low 60% range. For small birds, similar. The overall efficiency of both methods is lower, as you would expect. But the drone method is again, has a higher searcher efficiency than the pedestrian. For bats, the result is reversed. They have very wide error bars, which again relates to that low sample size. But the pedestrians outperform the drone AI method in bat detection. And if you lump small birds, medium birds, and bats all into one data set, you can see again the drone method significantly outperformed the pedestrian method. The differences are not huge in terms of searcher efficiency, but I think we can be pretty confident in saying that comparable searcher efficiency is obtainable with the drone AI method to pedestrian methods. The real difference comes in the level of effort. So we, recorded the amount of time that each searcher took to complete the survey plot. The mean survey coverage for pedestrian surveyors was almost 5 acres an hour, but the mean coverage for the drone AI method was almost 15 acres an hour. So in terms of the level of effort, the drone AI method is about a third the field effort as the pedestrian method. So comparable results, maybe even slightly better for the drone AI method in terms of searcher efficiency at a significantly lower level of effort. We performed a similar study with desert tortoises. We've developed a model for tortoises with an input of about 234 images, recall of 98%, precision of 0.84, a good model. We also developed a model for burrows. As many of you know, are aware, tortoise burrows are pretty distinctive in terms of their morphology, just due to the shape of the tortoise's shell. You can recognize the tortoise burrow pretty reliably, even from the air, given sufficient image resolution, and you can see some examples here. We developed a model to recognize these with about 457 input images, and again, the performance is very strong. We tested this method with a searcher trial, kind of similar to what we did with the avian trials. We conducted this in St. George, Utah, with a relatively small sample size of about 17 tortoise surrogates, and about 60 known burrows. So the survey area was surveyed intensively before the project to locate every burrow. So we knew where all the burrows were and we could measure the detection rate. And that's what's depicted on the map on the right. We did flights at 20, 30, 40, and 50 meters of flight elevation to sort of look at how the performance of the model presumably degraded as your flight elevation increased. Here are some of the results presented graphically. Again, the yellow rectangles are the actual drone photographs. The little red dots are tortoise detections. The blue dots are burrow detections. You can see that we found most of them since this is from 20 meters. And you can see it a little better on the box plot, similar to the last one I showed you. So the results for tortoises were the highest detection probability, to use the tortoise language, was at in the 20 meter flight elevation. It was about 0.67. It dropped off pretty quickly after that. 30 meters it dropped down to below 40%. 40 meters it dropped to below 20%. And so on. It's worth mentioning that the actual one reported mean detection probability for human surveyors has been published by the Fish and Wildlife Service using their training course, and that's 0.63. So the 0.67 detection probability for the drone AI method in this study is actually pretty comparable to what you would expect from a human surveyor, which is a good result. For burrows, the results were a little bit different. Detection probability actually peaked at 30 meters and then dropped off after that. So it looks like probably if you're looking for burrows, you can fly a little higher than if you're looking for tortoises. If you're looking for tortoises, you probably don't want to go above 20 meters. The real difference, again, is in the level of effort. Pedestrian surveyors average about 8 acres an hour with this kind of survey, 10 meter transects as per protocol. And the drone AI method averages almost 100 acres an hour. So a pretty drastic difference in the level of effort. So again, comparable performance in terms of detection probability at a much lower investment of effort. So in general, what can we conclude? The drone AI method has comparable detection rates to pedestrian surveys. In some cases a little bit better, in some cases a little bit worse. Drone AI surveys are much faster and more efficient in terms of field time. So we've measured about 3x for bats and small birds at 7 meters, about 12x for tortoises at 20 meters, and maybe as much as 25x for burrows at 30 meters. So comparable detection rates at a much lower level of investment. And in general, the efficiency advantage increases with target size and flight elevation. So that's my presentation. We're obviously very encouraged by these results, and we think that they clearly show the great potential that these methods have for making field data collection much more efficient and cost-effective for these kinds of resources for solar projects in the future. If you're interested in talking about this more, I'm always available. Please feel free to reach out to me. I'm always happy to talk about this stuff, and I really appreciate your attention. Thank you very much.